A carborane is a cluster composed of boron, carbon and hydrogen atoms. Like many of the related boranes, these clusters are polyhedra and are similarly classified as closo, nido, arachno, hypho, etc., based on whether they represent a complete polyhedron or a polyhedron that is missing one, two, or more vertices. Carboranes are a notable example of heteroboranes. Interesting examples of carboranes are the extremely stable icosahedral closo carboranes. These boron-rich clusters exhibit unique organomimetic properties with chemical reactivity matching classical organic molecules, yet structurally similar to metal-based inorganic and organometallic species. A prominent example is the charge-neutral C2B10H12 or O carborane with the prefix O derived from ortho, which has been explored for use in a wide range of applications from heat-resistant polymers to medical applications. The electronic structure of these compounds is best described by Wade-Mingo's rules for cluster molecules. Another important carborane is carborane acid, a chlorinated superacid H, which has an anion structure shown at right, dicarbodo-decarborane. The most heavily studied carborane is C2B10H12 M. p. 320 degrees Celsius. It is often prepared from the reaction of acetylene with decaborane. A variation on this method entails the use of dimethylacetylene dicarboxylate to give C2B10H1O2, which can be degraded to the C2B10H12. History: the 1,2 closo dicarbodo-decarboranes were reported simultaneously by groups at Olin Corporation and the Reaction Motors Division of Thiochal Chemical Corporation working under the U.S. Air Force and published in 1963. Heretofore, decaborane derivatives were thought to be thermally unstable and reactive with air and water. These groups demonstrated the unprecedented stability of the 1,2 closo dodecaborane group, presented a general synthesis, described the transformation of substituents without destroying the carborane cluster, and demonstrated the ortho-to-meta isomerization. Isomerization of dicarboranes. Ortho-dicarborane is the kinetic product from the addition of acetylenes to decarborane precursors. Upon heating at 420 degrees Celsius, the ortho-dicarborane rearranges to the meta-isomer. Upon further heating, one obtains paracarborane. Like arenes, carboranes also undergo electrophilic aromatic substitution. Dicarbolide. Numerous studies have been made on derivatives of the so-called dicarbolide anion 2-. The first metal dicarbolide complex was discovered by M. Frederick Hawthorne and co-workers in 1965. This anion forms sandwich compounds, referred to as bis, with many metal ions, and some exist in otherwise unusual oxidation states. The dianion is a nido cluster prepared by degradation of the parent dicarborane. For many practical syntheses, the monoprotonated dicarbolide salt B9C2H12 is isolated as its potassium salt, B10C2H12 plus 3CH3OH plus CoK B9C2H12 plus B3 plus H2O plus H2 to the monopotassium salt can then deprotonated with strong base, KB10C2H12 plus KHK2 B9C2H11 plus H2 bis often exhibit properties very different from the metallocene surrogates. For example, Ni-based bis cluster can be observed for the rare Ni-oxidation state of nickel. Some notable examples of potential applications of these complexes include catalysis, ion exchange materials for radioactive waste management, biologically active protease inhibitors, and chemically inert redox shuttles for dye-sensitized solar cells. Carbynes, carborane, or 1,2-dihydrocarborane, is an unstable derivative of orthocarborane with the formula B10C2H10. The hydrogen atoms on the C2 unit in the parent O-carborane are missing. The compound resembles and is isolable with benzene. A carborane compound was first generated in 1990 starting from O-carborane. The hydrogen atoms connected to carbon are removed by N-butylithium in tetrahydrofuran, and the resulting lithium dianion is reacted with bromine at 0 degrees Celsius to form the bromo-monoanion. Heating the reaction mixture to 35 degrees Celsius releases carborane, which can subsequently be trapped with suitable dienes, such as anthracene and furan in 10 to 25% chemical yield. Carboranes react with alkenes to benzocarboranes in an adaptation of the above-described procedure. O-carborane is deprotonated with N-butylithium as before and then reacted with dichlorodinickel to a nickel-coordinated carborane. This compound reacts with 3-hexene in an alkene trimerization to the benzocarborane. Single crystal X-ray diffraction analysis of this compound shows considerable bond length alternation in the benzene ring, ruling out aromaticity. Research. Carboranes have been explored as a source of boron in boron neutron capture therapy. They have also been examined in structural studies in crystallography. Carboranes have been used to make solid superacids. Solid superacid catalysts alleviate the need to dispose of spent acids, thus providing a significant environmental advantage over dissolved acids. The carborane superacid H is 1,000,000 times stronger than sulfuric acid. The reason for this high acidity is that the acid anion CHB11Cl11- is very stable and substituted with electronegative substituents. H is the only acid known to protonate C60-fullerene without decomposing it. Additionally, it is the only known anion capable of forming a stable, isolable salt with protonated benzene, C6H7+. In coordination chemistry, carboranes can be used as unique bulky ligand scaffolds. It was recently demonstrated that the same carbonyl moiety can act either as strongly electron-withdrawing or electron-donating substituent, depending on the positional attachment of the cluster to the heteroatom.